welcome back. Our next speaker is going to be Rick Bo, and he's going to be speaking about currently point-free topology.
I'd like to add my thanks to those of others, to Will for organizing the conference. I have a paternal fondness for the series because the series itself was organized by my colleagues Natasha Dobrinin and Nick Galatos 14 years ago. I happened to be on the committee, but my only contribution was to suggest the inclusion of point-free topology in the list of topics, and that's what I'll be speaking about today. Because the frames that I discuss will all be assumed to be completely regular, I thought I would start by reminding you what that looks like in frames. So on the board to my right, I have a definition of what complete regularity means. You'll say in a frame that one element is completely below another, this case A completely below B, provided there is a rationally indexed sequence of witnesses to that fact, with the property that if index P is below index Q in rational numbers, then witness W sub P is rather below witness W sub Q, where that's the usual notion of rather below written out there. This precisely captures the existence of a real valued function which takes 0 on the open set represented by A and takes value 1 on the this complementary closed set to B. Right? That's a fully equivalent formulation of that fact, purely in terms of the lattice. So in my talk, all of the frames will be assumed to be completely regular, and that will pose obstacles down the way, so it's important to keep that in mind. F is the category of completely regular frames and frame homomorphisms. And I'll be very interested in the points. Now, a point in a space is represented in the frame by the complementary open set. And that open set is a maximal element of the frame. So the family of points of a frame I can then identify with the family of maximal elements, and I'll signify that by max L. Now, the frame is spatial, meaning that it comes from the open sets of the space, precisely when every element of the frame is the meet of the maximal elements above it. So that's a fully equivalent condition, which I will take as the definition of spatiality, but in fact can be proven to be equivalent to the frame being the frame of open sets of some space, some Tikhonov space. Okay. The spatial frames, the category I will indicate by SF. That's the full subcategory category of the spatial frames. Now the relationship here is that any frame whatsoever has, any locale I should say, has a largest spatial sublocale. Right? And the passage from the frame to the sublocale is the passage which takes an arbitrary member of the frame and pushes it up to the meet of the maximal elements above it. Right? That then forms what's called the nucleus on the frame, whose fixed point sets is the sublocale representing the spatial part of the frame. And the kernel of that nucleus, meaning the set of elements which are mapped to the top by the nucleus, is simply the set of elements which have no maximal elements above them. Okay. I will refer to that surjection, it's actually a nucleus, as the spatial part of the frame, and I will use sigma sub L to indicate it. Now this is actually a functor, which means that it respects the maps. That is to say, any frame homomorphism, L to M, drops through the spatial nuclei to give a map M bar, which makes the diagram commute. So this passage to the spatial part is actually a reflection, and the nucleus is the reflector for the given frame. Not only is it. So it's a very nice situation But it leads us now to the point, to the next issue, because of course not all frames have points, and certainly even those that have points may not have enough points to be spatial. I'm going to say that a frame is pointless if it has no maximal elements. Okay? And I'm going to call the corresponding full subcategory PLF. A good example is the Adamos-Boolean algebras, right? They're obviously frames. They are in fact completely regular, and they have a tremendous amount of importance in this subject because of a very famous theorem of Isbell, to the point that every locale has a smallest dense sublocale. And in the case of a frame which is spatial, this is simply the regular open algebra, right? And the corresponding nucleus is the map which takes any open set to its regularization, the interior exposure. So you see these pointless frames are central to the theory, and therefore I'm asking that we very seriously try to understand how they interact with the spatial parts of the frame. So how do you take a point out of a frame? Sorry, how do you take a point out of space? Let's just ask that question. That's rather a silly question, of course, because you just do it. But the point here, the idea here is the passage from the space to a proper subspace, namely the subspace that you get by plucking out the point. And that's represented by the continuous function which embeds the subspace into the space. Now, in frame terms, of course, the frame map goes in the opposite direction. And that frame map associates to each open set in the space the largest open set in the subspace, which has the same meat with the point complement. So if A is a maximal element, then A arrow B is simply the biggest member of the overframe whose meet with A is A meet B. Okay? That's the heating arrow there. And the nucleus here is the map which pushes every element B to A arrow B. Okay? The term in the in this business for that map is that that's called the open quotient corresponding to the element A. Right? Usual notation is little o sub A for the nucleus and capital O sub A for the fixed point set. Of primary interest for our purposes will be the congruence. I'll use capital phi sub A for the congruence associated with that open congruence. Again, it's the set of all pairs which are associated by, which are identified by the nucleus. So let's now step back and ask the question of how we remove all of the points from a given frame. Well, the answer is now before us. We simply mod out the congruence, which is the join of these open congruences, right? That means, that seems to me to be unavoidably how one would go about this, and so we'll do it. The question that arises, of course, is what in the dickens is the nucleus which you achieve by doing that? And it turns out it has a very simple description. Perhaps not in terms of the nucleus, but in terms of the prenucleus. The prenucleus simply takes an arbitrary element of the frame and pushes it up to the join of the element with all of its immediate successors. Okay? Your successor means immediate successor. Okay? But this is not a nucleus, but it is a prenucleus, and so its fixed point set, namely all of the elements which have no successors, is a sublocale, and that sublocale I will designate pi L, and the nucleus I will designate pi sub L. And it's a perfectly good quotient that any frame has sitting there. Okay. I will refer to that arrow as the pointless part of the frame. So here's an example. Let's take the topology of the unit interval. And here I'm following Fred Dashiell in terms of his terminology. Let's say that an open set is punctured, open set U is punctured at the point X. If X is absent from the set, but when you adjoin X to the set, the result is still an open set, right? So this is, idea here is that the set as a whole at X, right? And then a set is unpunctured if it is not punctured at any point. So good examples of unpunctured sets are open intervals, for instance. But there are many, many others. For example, the complement of the Cantor set is unpunctured. And so this makes the point that the unpunctured sets in the real interval are in fact the pointless part of the topology of 0, 1. And this is much bigger than the regular open algebra. Witness the complement of the Cantor set, because certainly that's not regular open, it's dense. Right? So we have something before us which is strictly greater than the minimum dense sublocale, which is, I believe, of great intrinsic interest. All right, we now have two congruences corresponding to the spatial and the pointless parts. I'm calling them theta sub sigma and theta sub pi, respectively. One asks, what is the relation of these two congruences? And it is immediately apparent that they are disjoint. That is, their meet is the identity congruence. Right? In more prosaic terms, the pointwise meet of the nuclei is the identity. So that immediately suggests that every frame is a subdirect product of its pointless and spatial parts. That's simply true. Okay. But the situation is not yet symmetrical, because it turns out that although the spatial part is reflective, the pointless part is not. So we have to restrict the morphisms, and the way we do that is by passage to what I'm going to call skinny frame homomorphisms. Now, I can tell you what they are, but before I do, let me tell you what they amount to in spaces. These are simply the frame counterparts of the continuous functions which have scattered fibers. Okay? Scattered fibers. In frame terms, all you're doing is insisting that the frame map take maximal elements of the domain to members which may not be maximal in the codomain, but they're at least in the kernel, the pointless kernel of the codomain. In other words, by applying the pointless nucleus, you will eventually push them to the top. And you can classify, you can actually describe the attribute of being unpunctured in abstract terms if you like. And if you do so, then the corresponding equivalent condition is simply that M takes unpunctured elements of the domain to unpunctured elements of the codomain. In any case, all of this is to say that those are precisely the morphisms which drop through the pointless nuclei. So now we are going to pass to the non-full subcategories of frames, spatial frames, pointless frames, all with skinny morphisms. By the way, as an aside, let me just point out something which I think is amusing. This is not an aside, this is central. I have to check that they actually give me legitimate categories. And that becomes clear once you prove that isomorphisms, of course, are skinny, but all surjections are skinny. The composition of skinny morphisms is skinny, and if a composition is skinny and the first factor is surjective, then the second factor is skinny. So they have these nice properties. But the important one is that This is the category which makes the pointless part reflective. So this is the category we're interested in. And then it becomes clear that the congruence of the pointless part is precisely the join of the open congruences of the maximal elements. So this is just to reiterate what we said to start out. We have simply physically removed all the points by passing to the appropriate congruence. Now, there comes at this point into the picture a rather interesting factorization structure, and I'd like to describe that to you now. The morphisms in the category fractor E are those skinny surjections which have the feature that the morphism only identifies two elements of the frame if the two are identified by the join of the open congruences of those maximal elements which the morphism sends to the top of the codomain. That tells you that the morphism is only doing what it's forced to do by virtue of having taken certain maximal elements to the top. An equivalent formulation is that these are the morphisms whose congruences are the join of atoms in the congruence lattice. The companion class is a class fractor M of skinny sources, and those will be the sources for such that for every maximal element there's an index such that the corresponding morphism sends that maximal element to a destination below the top of the codomain. And then, again, I think it's rather amusing to observe that pointlessness can be characterized in terms of these classes as follows. Frame M is pointless if and only if every fractor M morphism out of it has a pointless domain, into it has a pointless domain, and every fractor E morphism out of it is an isomorphism. Those are alternative characterizations of pointlessness. And then the point, the objective of this is to show that, the skinny category is an EM category, which means that you have EM factorization of sources and the diagonalization property. Okay. But what that gives you is two important things. We had already remarked that the pointless frames were reflective in frames, but when you restrict to skinny morphisms, that becomes an E reflection. So the arrow is actually necessarily one of these fractor E morphisms. Okay. And likewise, the spatial arrow becomes one of these fractor M morphisms. Right? That's information that we didn't have before. But more than that, any morphism which happens to be a fractor E morphism and whose codomain is pointless is in fact necessarily the pointless part of the frame. That is a characterization of the pointless part in terms of the nature of the morphism involved and the nature of the codomain. Likewise, a morphism which happens to be a fractor M morphism and whose codomain is spatial is the spatial part of the frame. This is a characterization of the spatial part of the frame purely in terms of the nature of the morphism and the nature of the codomain. So back now again to this idea of a subdirect product. We've remarked that the two congruences are disjoint. They are not, however, complementary. Their joint is not the large trivial congruence. There's a good reason for that, and that is if you take the spatial arrow out of the frame, that's the sigma arrow, from L to sigma L, you can apply the pointless functor to that arrow and drop it down to the pointless parts, both of the original frame and of the spatial part. And in typical situations, the bottom arrow will not be trivial. Right? So That's simply to say that if you apply the two nuclei, one after the other, in this case, first the spatial nucleus and then afterwards the pointless nucleus, the result may not be trivial, right? You may have a non-trivial frame there. And what that bottom arrow then means is that this is what ties the pointless part to the spatial part. This is a connection between the two parts, which is trying to tell you something about how that frame is embedded in the subdirect product. For that reason, I named that arrow the ligature. It is what ties the two parts together. So this brings me to the notion of a subdirect EM product. What is that? Well, that's simply a subframe of the product such that the projection onto the first part is a fractor E surjection, and the surjection onto the second part is a fractor M surjection. So it's a special kind of subdirect product. If it happens that the E is pointless, that means that that projection is the pointless part of the frame. And if the M happens to be spatial, that means that that projection is the spatial part of the frame. So this immediately raises, I think, a question, and that is, if someone walks in the door, can, with a pointless frame E and a spatial frame M, can I build an L, which realizes this diagram? Actually, that's not quite the right question because of this arrow at the bottom. So suppose now we're given both the pointless frame E, the spatial frame M, and a frame surjection from E to pi M. That is the ligature. Suppose I'm given the pointless part, the spatial part, and the ligature. Can we then construct the L? And the answer is essentially yes, but with an interesting hitch. So here's the proposition. Suppose somebody walks in the door and gives us a pointless frame E and a spatial frame M and a frame homomorphism from E to pi M. That's my candidate for the ligature. And now look at all the members of the product of E times M for the feature that L applied to the left coordinate happens to come out to pi M applied to the right coordinate. That will identify a subframe of the product. Now, the problem here is that I have no reason to believe that that's completely regular. You see? It's just a subframe of the product. But complete regularity is a co-reflective property in frames. And so within L prime, there is a largest completely regular subframe, and I'm calling that L with no prime. That is the completely regular co-reflection of L prime. Okay? It may not be very big, but if it's big enough to have surjective projections, then I can say four things about it. I can say, and now these are all statements not about L prime, but about L, right? So it's predicated on the assumption that L is big enough to have surjective projections. But in that case, I can say that the maximal elements are what you would expect them to be. On the left coordinate top, on the right coordinate, are maximal elements of the spatial frame M. After all, the left coordinate is pointless. It has no maximal elements. Okay. The second thing I can tell you is that the projection onto M is one of these fractor M morphisms. So that means that that is the spatial part of L. And projection onto E is one of these fractor E morphisms. So that means that's the pointless part of L. And of course, the diagram commutes by construction. Okay. So in short, what this means is that L, should it have surjective projections, is the subdirect EM product of E and M, the ligature L. Okay. I will denote that by E cross M with the X subscripted by L. Right? So it's a special gadget sitting down inside the subdirect product. So there's the theorem. any frame at all is has the feature that the product morphism of pi sub L and sigma of L factors through the inclusion of this sub-object that we just built, and the initial factor is 1 to 1. So that's because L, being assumed completely regular, has an image which is completely regular, and therefore that image is big enough to have surjective projections, and the theorem then fires. So we can say about it that its image is in fact one of these subdirect EM products. Right? And that's now true in generality. Okay, so I'm now going to make a modest transition in the talk. That's sort of one piece of it. But if you think about it, there is another really very fundamental connection between the spatial part of a frame and the pointless part of a frame. And that is because if you have a maximal element of a frame with, say, pointless part E, then the family of all elements of E which fail to lie below the maximal element constitute a filter. Right? After all, these maximal elements are prime. So if two elements fail to be below A, then their meet also fails to be below A. Right? So there's a filter for you, and it's associated, as I say, with a maximal element. And one then proves that this is not just any filter, but it is, of course, proper, but also round. By which I mean, any element in this filter has another element in the filter which is completely below it in the sense of that definition. Right? So these are round filters. And not only that, but they have an additional feature, which is that the join of the pseudo-complements must go to the top. Right? So if you think of these as neighborhood filters, then the filter has to squeeze down to the point, right? Pseudo-complements have to join up to the top of the frame. Conversely, if you give me a pointless frame and one of the filters that I've just described there, then I can have a frame which has that given frame as its pointless part, and which has a maximal element. And the maximal element generates precisely the frame that you began with. That is precisely the filter that you began with. So every filter which has these two features arises in the fashion that I've indicated, from a maximal element in some frame containing the given frame as its pointless part and the maximal element as well. My term for filters with these two features is that they're regular, and they exist in profusion. For example, every maximal proper round filter is regular, and maximal proper round filters exist by Zorn's lemma. So every round filter is contained in many, many maximal round filters, and all of those are regular. So every frame has a huge number of these regular filters, right? And each one of them is a candidate for the location. This is how I think of it. I think of the filter as telling you the location of the point in the pointless part. Right? So every point is located in the pointless part by a specific round filter associated with it in this fashion. Right? Last thing I want to say is, if you have two different maximal elements, they will give rise to regular filters which are independent in the sense that the two filters will contain disjoint elements. Right? So these as I say, many points give you filters, but the filters are all independent of one another in the sense of containing disjoint elements. So the theorem here is that if you start off with finitely many of these regular filters, presuming they're independent of one another, and a pointless frame, then there is precisely up to isomorphism exactly one atomless frame L having the given pointless frame as its pointless part, and exactly n maximal elements which precisely generate the regular filters in the fashion that we've indicated. Okay. My term for the family of these regular filters which arise from the points is, I'm calling them the spatial support of the frame. And by the way, how am I doing on time? Have I got?
We can take a couple of minutes more.
Okay, I'm just about done. So I guess at this point, what I'm trying to indicate is that the information we have before us is that there is this pointless part which is floating around somehow, and we're trying to insert points into it in a systematic fashion. But the reason we can do that is that the filters that are given to us by way of this spatial support are simply locating the points in the pointless part, right? So, however, there are technical problems that arise here. What I can say is that if you give me a pointless frame E and an independent family of these regular filters, and if I know in advance that they come from a frame, then there's a biggest frame that they come from. Right? But what I'd like to do is to be able to tell you exactly which independent families of regular filters come from a frame, and that I cannot do. However, I can tell you that there is a cardinality limit, right? So for a given pointless frame, you might ask, how big is the biggest spatial frame that can have this guy as its pointless part? And the answer is, there is a cardinality bound. What is the cardinality bound? Well, this pointless frame has a checkstone compactification, and the number of points of that checkstone compactification is an upper bound on the number of points in any spatial frame having this point-free part. So there's a limit to how many points you can put into a given pointless frame. And the real question that I'd like to pose to you is, if I give you a pointless frame, can you tell me that there is a spatial frame out there with that as its pointless part? I have a number of other results along these lines which indicate the influence of the spatial support. For instance, the frame in question is compact if and only if the independent family is maximal among independent families, etc. These are descriptive results, but the fundamental issue is the one that I just mentioned. I give you a pointless frame, you tell me whether or not there's a spatial frame with that as its pointless part. Thank you very much.
Are there any quick questions for Richard? Thank you.